So now that we have seen the basics about how to define classes and objects, let's define an interesting data structure. Suppose we want to implement our own version of a list. So a list is basically a sequence of nodes, and each node in the sequence stores a value and points to the next node. So in order to go through the list, we have to start at the beginning and walk following these pointers till we reach the last pointer, which points to nothing. So if we have a list of the form v1, v2, v3, v4 in Python notation, then this is how we would imagine it is actually represented. There are 4 nodes. The list L itself, which we have set up, points to the first node in the list. v1 points to v2, v2 points to v3, and v3 points to v4. The final node points to nothing, and that indicates we have reached the end of the list. So in this representation, what would the empty list look like? Well, it's natural to assume that the empty list will consist of a single node which has both the value and the next node pointer set to none. Whereas, for instance, a singleton would be a single node in which we have the value v1 and the next set to none. So this is the convention that we shall follow for our representation of a list. So notice that unless we have an empty list with a single node none, none, no other node in a list can have value none. Okay? So this is something that we will implicitly assume and use, that checking for the value none will tell us it's an empty list, and we will never find a none in the middle of a list. So we distinguish between a singleton and an empty list purely based on the value. Both of them consist of a single node. Now the reason that we have to do this is because actually Python doesn't allow us to create an empty list. If we say something like L is equal to none and we want this to denote the empty list, the problem is that none doesn't have a type as far as Python's value system concerned. So once we have none, we can't apply the object functions we are going to create for this list type. So we need to create something which is empty of the correct type. So we need to create at least one node. And that's why we need to use this kind of a representation in order to denote an empty list. So here is the basic class that we're going to use. So it's a class node. So inside each node we have 2 attributes, value and next, as we said. And remember that self is always used with every function to denote the object under consideration. We will use this default scheme that if we don't say anything, we create an empty list. So the init value, so this should be init val. So the initial value is by default none, unless I provide you an initial value, in which case you create a list with that value. And because of our assumption about empty list, all we need to do to check whether a list is empty is to check whether the value at the initial node is none or not. So we just take the list we are pointing to and look at the very first value, which will be self.value, and ask whether it's none. If it is none, it's empty. If it's not none, it's not empty. Okay. So here is a typical thing. So we say L1 is equal to node. This creates an empty list because it's not provided any value. So the default initial value is going to be none. If I say L2 is equal to node 5, this will create a node with the value 5. So it will create the singleton list that we would normally write in Python like this. So if I ask whether L1 is empty, the answer will be true. If I ask whether L2 is empty, the answer will be false because self.value is not none. Now once we have a list, what we would like to do is manipulate it. So the first thing that we might want to do is add a value at the end of the list. So if the list is already empty, then we have a single node which has value none, and we want to make it a singleton node, a singleton list with value v. So we want to go from this to this. Okay. So remember that in a singleton node, we just have, instead of none, we have the value v over here. So that's all we need to do. We need to just replace the none by v. If we are at the last element of the list, and we know that we are at the last element of the list because the next value is none, then what we need to do is create a new value. So we walk to the end of the list, right? And then we reach none. So now we create a new element here with the value v, and we make this element point to it. So we create a new element, the node v, and set the next field of the last node to point to the new node. And if this is not the last value, then, well, we can just recursively say to the rest of the list, treat this as a new list starting at the next element, take the next element and recursively append v to that. So this gives us a very simple recursive definition of append. So we take append and we want to append v to this list. So if it is empty, then we just set the value to v. So this just converts the single node with value none to the single node with value v. Otherwise, if we are at the last node, that is self.next is none, then we create a new node with the value v and we set our next pointer to create a new node. Remember, when we create a new node, the new node automatically is created by our init function with the next none. So we would now create a new node which looks like v and none, and we will set our next pointer to point to it. And the final thing is that if it is not none, then we have something else after us. So we go to that next element self.next, and with respect to that next element, we reapply the append function with the value v. So this is the recursive call. So we have been abundantly careful in making sure that this is parsable. So we have put this bracket saying that we take the object self.next and apply append to that. Actually, Python will do this correctly, so we need not actually put the bracket. So we can just write self.next.append v, and Python will correctly bracket this as self.next.append. So this dot is taken from the right. Now, instead of recursively going to the end of the list, we can also scan the end of the list till the end iteratively. So we can write a loop which keeps traversing these pointers until we reach a node whose next is none. So if the list is empty as before, we replace the value none by v. Otherwise, we scan the list till we reach the last element. And then once we reach the last element, as in the earlier case, we create a new node and make the last element point to it. So this gives us an append which is iterative. So we call it append I just to indicate it's iterative. So the first part is the same. If the current list is empty, then we just set the value to be v and we return. Otherwise, we now want to walk down the list, right? So we set up a temporary pointer to point to the current node that we are at. And so long as the next is none, we keep shifting temp to the next value. So we just write a loop which says while temp.next is not none, just keep going from temp to temp.next. So just keep shifting temp. Finally, when we come out of this loop at this point, okay, we know that temp.next is none. Right? So this is the condition under which we exit the loop. So we have reached the node temp is now pointing to the last node in the current list. At this point, we do exactly what we did in the recursive case. We create a new node with the value v, and we make this last node point to this new node. So we reset next of temp from none to the new node. So what if we don't want to append, but we want to insert? Now it looks normally that insert should be easier than append, but actually insert is a bit tricky. So by insert, we mean that we want to put a value at the beginning. So we want to put a node here which has v and make this point here. So this is what we want to do. Now the problem with this really is that after we create a new node, we cannot make this point here and this point here. There's no problem in making the new node point to v1. But if we reassign the value of L, or inside a object, if we reassign the value of self, then this creates a completely different object. So we saw this when we were looking at how parameters are passed and mutable values are passed. We said that if we pass a mutable value to a function, so long as we don't reassign that thing, any mutation inside the function will be reflected outside the function. But if we reassign to the function, to the list or dictionary inside the function, we get a new copy. And then after that, any change we make is off. So same way, if we reassign L or self to point to a new node, then we will lose the connection between the parameter we pass to the function and the parameter we get back. So we must be careful not to make L point to this thing. So we cannot change where L points to. So how do we get around this problem? We have created a new node, we want to make L point to it, but we are not allowed to do so, because if we do so, then Python will disconnect the new L from the old L. So there is a very simple trick. What we do is we don't change the identity of the node, we change what it contains. So we know now that v1 is the old first node and v is the new first node, but we can't make L point to the new first node, so we exchange the values. So what we do is we replace v1 by v and v by v1. So now the values are swapped, and we also have to do a similar thing for the what is pointing where. So L is now pointing to v as the first node, but now we have bypassed v1, which is a mistake. So we must now make the first node point to the new node and the new node point to the old second node. So by doing this kind of plumbing, okay, what we have ensured is that the new list looks like we have inserted a V before the V1, but actually we have inserted a new node in between V and V2, and we have just changed the links to make it appear as though the new node is second and not first. So here is the code for insert. So as usual, if you have an empty list, insert is easy. We just have to change none to V. So insert and append both behave the same way. With an empty list, we go from the empty list to the list V. It doesn't matter whether you're inserting or appending. Otherwise, we create this new node and then we do this swapping of values between the current node that self is pointing to, that is the head of the list, and the new node. So we exchange the values. We set self.value to new node.value and simultaneously new node.value to self.value using this Python simultaneous assignment. And similarly, we take self.next, which was pointing to the next node, and make it point to the new node. And the new node instead should point to what we were pointing to earlier. So new node.next is self.next. So this is how we insert. And insert, as we saw, is a little bit more complicated than append because of having to handle the initial way in which L points to the list or self points to the list. What if we want to delete a node? So how do we specify to delete a node? Well, we specify it by value, but let's just suppose we want to delete, say, the second node in this list. Now, how would we delete it? Well, again, just as we did insert, we would do some replumbing or reconnection. So we take the node that we want to delete and we just make the link that points to V2 bypass it. Right? So we take the link from V1 and make it directly point to V3. So in a sense, all the delete requires us to do is to reassign the pointer from before the deleted node to the pointer after the deleted node. It actually does not physically remove that object from memory, but it just makes it inaccessible from the link array. So we provide a value V and we want to remove the first occurrence of V. So we scan the list for the first V. Now notice that in this plumbing procedure, we need to be at V1 in order to make it point to V3. So if we want to delete the next node, then we are in good shape because we can take the next dot next and assign it to the current next. So we should look one step ahead. If we are already at V2, then we have gone past V1 and we can't go back to V1 easily the way we have set up our list because it only goes forwards. We can't go back to V1 and change it. So what we will actually do is we will scan by looking at the next value. So if the self.next.value is V, that is the next node is to be deleted, then we bypass it by saying the current node's next is not the next node that we had, but the next node's next. So self.next is reassigned to self.next.next, bypass the next node. So as before, like with insert, the only thing we have to be careful about is if we have to delete actually the first value in the list. So if we want to delete the first value in the list exactly like we had with insert, the natural thing would be to now say that L should point to the second value in the list. But we cannot point L there because if we reassign the node that L points to, then it will create a new object and it will break the connection between the parameter we pass and the thing we get back. So we use the same trick, right? What we do is we copy V2, the value V2 from the next node, and then, so we just copy this value from here to here, and then we delete V2. Okay? So we wanted to delete the first node. We are not allowed to delete the first node because we can't change what L points to. So instead, we take the value in the second node, which was V2, copy it here, and then pretend we deleted V2 by making the first node point to the third node. So here is a part of the delete function. So first of all, if we were looking for V, right, and then we don't find it, so sorry, in this code it's called X, so this is deleting value X if you want, right? If we say that the list is empty, then obviously we can't delete it because delete says if there is a value of this a node with value X, then delete it. Okay? So if it is empty, we do nothing. Otherwise, if the self.value is X, the first node is to be deleted. Okay? Then if there's only one node, then we are going from X to empty. This is easy, right? So if there is no next node, right? If we have only a singleton, then we just set the value to be none and we are done. So this is the easy case. But if it is not the first node, I mean it is the first node and this is not also the only node in the list, then what we do is we do what we said before. We copy the next value. We pretend that we are deleting the second node. So we copy the second value into the first value, and we delete the next node by bypassing. So this is that bypass, right? So this is part of the function. This is the tricky part, which is how do you delete the first value? If it is only one value, make it none. If not, bypass the second node by copying the second node to the first node. And if this is not the case, then we just walk down and find the first X to delete. So we start, as this is like our iterative append, we start pointing to self, and so long as we have not reached the end of the list, if we find the next value is X, then we bypass it, right? And if we reach the end of the list and we haven't found it, we do nothing, we just have to return. In this case, it's not like append, where when we reach the end of the list, we have to append. Here, if we don't find an X by the time we reach the end of the list, then there's nothing to be done. So just for completeness, here is the full function. So this was the first slide we saw, which is the case when the value to be deleted is in the first node. And this is the second case when we walk down the list looking for the first X to delete. So just like append can be done both iteratively and recursively, we can also delete recursively, which is, if it is the first node, we handle it as a special way by moving the second value to the first and bypassing it as we did before. Otherwise, we just point to the next node and ask the next node, the list starting at the next node, what is normally called the tail of the list, to delete V from itself. Okay? So the only thing that we have to remember in this is that if we reach the end of the list and we delete the last element, right? So supposing it turns out the value V to be deleted is here. So we come here and then we delete it. What we'll end up with is finding a value none being, because when we delete it from here, it's as though we take a singleton element V and delete V from a singleton and we'll create none. So this is the base case, right? So if we are recursively deleting as we go, whenever we delete from the last node, it's as though we are deleting from a singleton list with value V. And we are not allowed to create a value none at the end. So we have to just be checked when we create the next thing. If we delete the next value and its value becomes none, then we should remove that item from the list. So this is the only tricky thing, that when we do a recursive delete, we have to be careful. After we delete, we have to check what has happened. Okay? So this part is the earlier part. And now this is the recursive part. The recursive part is fairly straightforward. So this is the first part is when you delete the first element from a list. For the recursive part, we check if self.next is equal to none, then we delete recursively. That's fine. So this is the delete call. Now, after the delete is completed, we check whether the next value has actually become none. Have we actually ended up at the last node and deleted the last node? If so, then we remove it. So this we can either write self.next is equal to self.next.next, or we could even just write self.next is equal to none, which is probably a cleaner way of saying this, because it can only happen at the last node. So we make this node the last node. Okay. Remember, if the next node is none, its next node will also be none. So this has the same effect. Self.next.next must be none. So we can also directly assign self.next equal to none, and it would basically make this node the last node. So the only thing that to remember about recursive delete is when we reach the end of the list and we have deleted this list, this becomes none, then we should terminate the list here and remove this node from it. Finally, let's write a function to print out a list so that we can keep track of what's going on. So we will print out a list by just constructing a Python list out of it and then using str on the Python list. So we want to create a Python list from the values in our list. So we first initialize our list that we are going to produce with the empty list. If our list, the node itself has nothing, then we return the string value of the empty list. Otherwise, we walk down the list and we keep adding each value using the append function, right? So we keep appending each value that we have stored in each node, building up a Python list in this process, and finally we return whatever is the string value of that list. So let's look at some Python code and see how this actually works. So here we have code which exactly reflects what we did in the slides. We have chosen to use the recursive versions for both append and delete. So we start with this initialization, which sets the initial value to be none by default, or otherwise V as the argument provided. Then isEmpty just checks whether self.value is none. We had written more compact form in the slide by saying just return self.value equal to none, but we have expanded it out as an if statement here. Now this is the append function, right? So append just checks, right? If the current node is empty, then it puts it here. Otherwise, it creates a new node. If we have reached the last node, it creates a new node and makes the last node point to the new node. Otherwise, it recursively appends. Right? Then we have this insert function here. So this insert function, again, if it is empty, then it just creates a singleton list. Otherwise, it creates a new node and exchanges the first node and the new node. Right? So this particular thing here is the place where we create this, swap the pointer so that what self points to doesn't change, but rather we create a reordering of the new node and the first node. So the new node becomes the second node and the first node now has the value that we just added. And finally, we can come down to the recursive delete. Okay, so the recursive deletes again says that if the list is empty, then we do nothing. Otherwise, if the first value is to be deleted, then we have to be careful and we have to make sure we delete the second value by actually copying the second node into the first. And finally, if that is not the case, then this will recursively delete. But then when we finish the delete, we have to delete a spurious empty node at the end of the list in case we have accidentally created it. So these two lines here, just make sure that we don't leave a spurious empty node at the end of the list. And finally, we have this str function, which creates a Python list from our values and eventually returns a string representation of that list. So if we now run this by importing, then we could say, for instance, that L is a list with value 0, and if we say print L, then we will get this representation 0 to L. We could, for instance, put this in a loop and say for I in range 1, say 11, L dot append I. Okay, and then if we at this point print L, then we get 0 to 10 as before. Now we say L dot delete 4, for instance, and we print L, then 4 is gone, and so on. Right? If we say L dot insert 12 and print L, then 12 is at the beginning. Right? So you can check that this works. Notice that we are getting this empty bracket. This is the return value. So when we wrote this return, we wrote with the empty argument, and then we get this empty tuple. You can just write a return with nothing, and then it won't display this funny return value. But what is actually important is that the internal representation of our list is correctly changing with the functions that we have written.